Gel, Wikipedia audio. A gel is a liquid jelly-like material that can have properties ranging from soft and weak to hard and tough. Gels are defined as a substantially dilute cross-linked system, which exhibits no flow when in the steady state. By weight, gels are mostly liquid, yet they behave like solids due to a three-dimensional cross-linked network within the liquid. It is the cross-linking within the fluid that gives a gel its structure and contributes to the adhesive stick. In this way, gels are a dispersion of molecules of a liquid within a solid in which liquid particles are dispersed in the solid medium. The word gel was coined by 19th century Scottish chemist Thomas Graham by clipping from gelatin. Note 1. A gel has a finite, usually rather small, yield stress. Note 2. A gel can contain a covalent polymer network, e.g., a network formed by cross-linking polymer chains or by nonlinear polymerization, a polymer network formed through the physical aggregation of polymer chains, caused by hydrogen bonds, crystallization, helix formation, complexation, etc., that results in regions of local order acting as the network junction points. The resulting swollen network may be termed a thermoreversible gel if the regions of local order are thermally reversible, a polymer network formed through glassy junction points, e.g., one based on block copolymers. If the junction points are thermally reversible glassy domains, the resulting swollen network may also be termed a thermoreversible gel. Lamellar structures including mesophases, e.g., soap gels, phospholipids, and clays, particulate disordered structures, e.g., a flocculent precipitate usually consisting of particles with large geometrical anisotropy, such as in V2O5 gels and globular or fibrillar protein gels. Gels consist of a solid three-dimensional network that spans the volume of a liquid medium and ensnares it through surface tension effects. This internal network structure may result from physical bonds or chemical bonds, as well as crystallites or other junctions that remain intact within the extending fluid. Virtually any fluid can be used as an extender, including water, oil, and air. Both by weight and volume, gels are mostly fluid in composition and thus exhibit densities similar to those of their constituent liquids. Edible jelly is a common example of a hydrogel and has approximately the density of water. Composition. Polyionic polymers are polymers with an ionic functional group. The ionic charges prevent the formation of tightly coiled polymer chains. This allows them to contribute more to viscosity in their stretched state, because the stretched-out polymer takes up more space. This is also the reason gel hardens. See polyelectrolyte for more information. A hydrogel is a network of polymer chains that are hydrophilic, sometimes found as a colloidal gel in which water is the dispersion medium. Hydrogels are highly absorbent natural or synthetic polymeric networks. Hydrogels also possess a degree of flexibility very similar to natural tissue, due to their significant water content. The first appearance of the term hydrogel in the literature was in 1894. Common uses for hydrogels include scaffolds in tissue engineering. When used as scaffolds, hydrogels may contain human cells to repair tissue. They mimic 3D microenvironment of cells. Hydrogel-coated wells have been used for cell culture, environmentally sensitive hydrogels. These hydrogels have the ability to sense changes of pH, temperature, or the concentration of metabolite and release their load as result of such a change. Sustained release drug delivery systems, providing absorption, desloughing, and debriding of necrotic and fibrotic tissue. Hydrogels that are responsive to specific molecules, such as glucose or antigens, can be used as biosensors, as well as in DDS, disposable diapers where they absorb urine, or in sanitary napkins, contact lenses, EEG and ECG. Medical electrodes using hydrogels composed of cross-linked polymers, water gel explosives, rectal drug delivery and diagnosis, encapsulation of quantum dots, breast implants, glue, granules for holding soil moisture in arid areas, dressings for healing of burn or other hard-to-heal wounds. Wound gels are excellent for helping to create or maintain a moist environment, reservoirs in topical drug delivery, particularly ionic drugs, delivered by iontophoresis, materials mimicking animal mucosal tissues to be used for testing mucoadhesive properties of drug delivery systems. Common ingredients include polyvinyl alcohol, sodium polyacrylate, acrylate polymers and copolymers with an abundance of hydrophilic groups. Natural hydrogel materials are being investigated for tissue engineering. These materials include agarose, methylcellulose, hyaluronan, elastin-like polypeptides and other naturally derived polymers. Hydrogels show promise for use in agriculture, as they can release agrochemicals including pesticides and phosphate fertilizers slowly, increasing efficacy and reducing runoff, and at the same time improve the water retention of drier soils such as sandy loams. An organogel is a non-crystalline, non-glassy thermoreversible solid material composed of a liquid organic phase entrapped in a three-dimensionally cross-linked network. The liquid can be, for example, an organic solvent, mineral oil, or vegetable oil. The solubility and particle dimensions of the structurant are important characteristics for the elastic properties and firmness of the organogel. Often, these systems are based on self-assembly of the structurant molecules. Organogels have potential for use in a number of applications, such as in pharmaceuticals, cosmetics, art conservation, and food. Azerogel/ZRODL/ is a solid formed from a gel by drying with unhindered shrinkage. Zerogels usually retain high porosity and enormous surface area, along with very small pore size. When solvent removal occurs under supercritical conditions, the network does not shrink and a highly porous, low-density material known as an aerogel is produced. Heat treatment of a zerogel at elevated temperature produces viscous sintering and effectively transforms the porous gel into a dense glass. Nanocomposite hydrogels are also known as hybrid hydrogels, can be defined as highly hydrated polymeric networks, either physically or covalently cross-linked with each other and/or with nanoparticles or nanostructures. Nanocomposite hydrogels can mimic native tissue properties, structure, and microenvironment due to their hydrated and interconnected porous structure. A wide range of nanoparticles, such as carbon-based, polymeric, ceramic, and metallic nanomaterials can be incorporated within the hydrogel structure to obtain nanocomposites with tailored functionality. Nanocomposite hydrogels can be engineered to possess superior physical, chemical, electrical, and biological properties. Many gels display thixotropy; they become fluid when agitated, but resolidify when resting. In general, gels are apparently solid, jelly-like materials. It is a type of non-Newtonian fluid. By replacing the liquid with gas, it is possible to prepare aerogels, materials with exceptional properties including very low density, high specific surface areas, and excellent thermal insulation properties. Polyionic polymers. Some species secrete gels that are effective in parasite control. For example, the long-finned pilot whale secretes an enzymatic gel that rests on the outer surface of this animal and helps prevent other organisms from establishing colonies on the surface of these whales' bodies. Hydrogels existing naturally in the body include mucus, the vitreous humor of the eye, cartilage, tendons, and blood clots. Their viscoelastic nature results in the soft tissue component of the body, disparate from the mineral-based hard tissue of the skeletal system. Researchers are actively developing synthetically derived tissue replacement technologies derived from hydrogels, for both temporary implants and permanent implants. A review article on the subject discusses the use of hydrogels for nucleus pulposus replacement, cartilage replacement, and synthetic tissue models. Many substances can form gels when a suitable thickener or gelling agent is added to their formula. This approach is common in manufacture of wide range of products, from foods to paints and adhesives. In fiber optics communications, a soft gel resembling hair gel in viscosity is used to fill the plastic tubes containing the fibers. The main purpose of the gel is to prevent water intrusion if the buffer tube is breached, but the gel also buffers the fibers against mechanical damage when the tube is bent around corners during installation, or flexed. Additionally, the gel acts as a processing aid when the cable is being constructed, keeping the fibers central whilst the tube material is extruded around it. Types: hydrogels, organogels, xerogels, nanocomposite hydrogels. Properties: animal-produced gels. Applications: